This is chapter 3 in digital signal processing, number 1, and it says construct the zero pole plots. So the first thing that we're going to do is we're going to break the top up into zeros and then break the bottom into poles. So we have z squared plus 1, so we can change that to z squared plus 1 squared. And that can be broken into another set. I'm just trying to break them down right now. So for this one, I can break it into z squared minus the cube root of 3 squared. So taking the cube root and then squaring it doesn't change the number, but it helps it put it in a different form for us. And this is squared. So now we can break that set of parentheses on the top. So we'd have z plus 1 and z plus 1. And then on the bottom we can break that into z minus the square root of 3 and so that was z plus the square root of 3, and then all of that is going to be squared. So we want to find the roots of these, and now that they're in parentheses it's easier to find the roots. So the root of z plus 1, we're going to set z plus 1 equal to 0 and then solve for z. So we know that that root is going to be equal to -1. Now we're going to do the same thing with the z minus the square root of 3. So we have z minus the square root of 3 is equal to 0. So we have z is equal to the square root of 3. And then we have the other one that is z plus the square root of 3 is equal to 0. So we have z is equal to square root of 3 negative, or negative square root of 3. So these ones on top that we found the roots for, these are going to be the zeros. And you can think of this because if we have a 0 on the top, which is what we're solving for the point at which z goes to 0. If we have a 0 on top of any number, it equals a 0. And the bottoms are our poles, and you can think of that because if we have any number divided by 0, it's going to be a really large number, and it's going to be a pole if we do it on a graph, like an XY graph, it's going to go up to infinity. So we call that a pole because it creates almost a pole-like vertical slope up towards infinity. So the zeros that we found were both -1. So we have two zeros at -1. And on the bottom, we found that we had a positive 3, square root of 3, and a negative square root of 3. So we have a 1 pole at square root of 3 and 1 pole at negative square root of 3. Now we don't actually have 1 pole for both of these bottom ones because if we noticed, we forgot the square root on the very outside here. So this square root makes this so that we have 2 poles here and 2 poles here. Makes each one of these 2 poles, because you could go ahead and distribute that 2 inside the parentheses, and you'd have 1 for this one and 1 for that one. So we always have to have the same amount of poles as we do zeros, and since altogether we have 4 poles and we have 2 zeros, it means we're missing 2 of our zeros. So in order to find those missing zeros, we're going to take the original function, which was this up here, and we're going to take the limit as z goes to infinity. So we have the limit as z approaches infinity. And we don't need to really worry about this entire thing since we are taking the limit as z goes to infinity. We just take the numerator on the top and the highest numerator on the bottom. So this 2 would go to this one, so we actually have a numerator exponential number of 4. So we have z to the 2 over z to the 4. And as that goes to infinity, we're left with 1 over z to the 2. So now we can see that as we go to infinity, so at infinity, we have 2 zeros. And we can tell that these are zeros because when we're dividing by a really large number here, we're going to get 0 because any number divided by infinity is going to be 0. So at infinity, we have 2 zeros. And we can tell that we have 2 of them, not only because we're missing 2 zeros, but because of this number that is remaining right here is a 2, and it indicates we have 2 zeros, and that's as z goes to infinity, and that is why they're at infinity.